Now we're going to look at the second variation of a functional which has got multiple independent functions. So we're going to start off with two independent functions. Now we've seen this equation here before and we derived that in a previous video, and this was the second variation of a simple functional. So the functional would have been of the form f of our x, y and y dash. But now what we're going to do is we're going to, rather than derive this here for a simple functional, we want to derive that same second variation but for a functional with two independent functions. So for example, what we would have then would be our new functional would be of the form f of x, and we would have our y1, which is y is a function of x, and we would have y2 as a function of x as well. And then we would have our y1 derivative, which is a function of x, and our y2 derivative, which is a function of x. So this is our functional form which we've seen in the previous video. But as we mentioned before, we're going to replace our independent variable x with the independent variable t instead. So rather than going from x0 to x1, we'll go from t0 to t1. And rather than talking about these independent functions y1 and y2, we'll replace our y's with the values of our q's, because you tend to see these values for q's used in mechanical problems. So our functional form is actually going to be of this form here. So we're going to have our function of our q1, q2, q1 derivative, q2 derivative, and those are all functions of our independent variable t. Now we're not going to go ahead and derive the equation here, we're just going to state it. I'll leave the derivation in the resources section whenever I've created that, and you'll be able to have a look at that derivation. So I've really just got the derivation stated below. So let's replace the value q1 in this instance just with the value of 1, and say our q2 is the value 2, our q1 dash is a value 3, and our q dash is a value of 4. So it means that whenever we write out the differentiation, we can shorten it in the following manner. So for example, rather than writing partial squared f by partial q1, and that should actually be squared at the other side, so just let me quickly rub that out. So that squared term shouldn't be there, it's q1 and it would be squared up here. Okay, so rather than writing it out in this format here, we could just simply write this as f11, because it would be the q1 times the q1, so it would be partial q1 squared. So the top line would remain the same, partial squared f, but the bottom line would be given by the value of our 1, which is q1 times q1. So another example would be f12, so the top line would remain the same, but f12, well, f1 is going to be q1, and f2 is going to be q2, so we'd simply have our q1, q2. So if we had something like f14, then it would be partial squared f by partial q1 times partial q2 derivative. So that allows us to simplify all of the different differentiations that we can do. Now whenever we've worked through, and as I said, you'll see in the appendix section the derivation, but the derivation for this new second variation of our more complicated functional is going to be of this form here. Now I'm not going to read it out, you can see for yourself, and we're going to use this particular functional form. So let's continue with this on the next page. So again, there's no proof here, this is purely a statement. The Legendre test for a functional with two independent functions, which we've just seen in the previous page, if the range t0 to t1 is small, and if f22 and f44 have got constant signs on t0 and t1, and also if f22 times f44 is greater than f24 squared, then f22 greater than 0 will ensure we have an extremum that is a minimum, and if f22 is less than 0, it will ensure we've got an extremum that is a maximum. Now, again, we're not going to go through and prove all of this. It would be an awful lot of mathematics that we'd have to go through to prove it, and we're really at the very edge of what we need to know for our course on the calculus of variations. So it's really just a bit of a statement just to show you that that this type of derivation has been done in the past, and all of this has already been worked out. Now, if we were to extend this rather than having the two independent functions, if we had extended it to n independent functions, then again the Legendre test would tell us that as long as the range to t0 to t1 is small, and in this instance here, if partial squared f by partial q r derivative squared is a constant sign on the range t0 and t1, where that r is 1, 2, 3 up to n, and this here is satisfied as well. So I'm not going to read this out, you can see it for yourself. And we're assuming that r doesn't equal s, and again in r and s range from 1, 2, 3 up to some value of n. Then if the partial squared f by partial q r derivative squared is greater than 0, we're going to have a minimum. And if partial squared f by partial q r derivative squared is less than 0, we're going to have a maximum. So this is the alternative for the n independent variables. So a bit dry this video because we're not going through any proofs, it's just the statements. So thank you for listening. I'll get you on the next video. Goodbye.